All right, we are now on part two. So, if you remember in part one, for our M&Ms, we got 50 M&Ms. We randomly selected 50. You might have different numbers than me if you did this along with me. If not, if you just used what I had, then we got 8 brown, 5 yellow, 3 orange, 7 green, 7 blue, and 20 red. Now, we have what M&Ms advertises here, and we figured out if 13% of M&Ms are really supposed to be brown, out of 50, I'd expect 6.5. If 14 were supposed to be yellow, I'd expect 7 yellow. If 20% were supposed to be orange, 10 are supposed to be orange. And I went through in the first video how I calculated all these. I also calculated a chi-square test statistic of 36.06. And again, I did that in the previous video. If you want to go back to that to figure out where this came from, you can do that. What we're going to go over now are the conditions we need for a hypothesis test to make sure we can run this. And then we're going to go over how we can find our p-value and ultimately come up with some sort of conclusion. Now, for our first condition when doing a chi-square goodness of fit test, you want to make sure it's random. Now, in this case, it was random. How do I know? I shook my bag of M&Ms. I had a pretty big bag. I don't know about you guys, but maybe you randomly selected a bag of M&Ms if you had a smaller one. Like I had a really big one. Randomly select the M&Ms. So I'm going to put that for my random here. Next one we have here, large counts. Now, large counts are typically we've been dealing with 10. In this case, it all has to do with 5. We want to make sure all of our expected counts, I'll put that here, all expected counts need to be greater than or equal to 5. So if I go up to here and I take a look at my expected values, 6.5, greater than 5. 7, greater than 5. 10, greater than 5. 8, greater than 5. 12, greater than 5. And 6.5, greater than 5. This is all based on expected values. That's important here. I do not do it based on what I see. If I did based on what I saw, then I wouldn't be able to do this test because I only had 3 orange M&Ms. Again, it's all based on what you expect. You want to make sure you're expecting to see 5 or greater. In this case, I did. So again, for our conditions, we've got random, large counts. And in this case, for large counts, remember, it's all greater than or equal to 5. Part of it has to do with, since you're dealing with categorical variables, you're going to have more categories going on. It's not necessarily just binary of yes or no. In this case, we have 6 different possibilities for a categorical variable of color. We have brown, yellow, orange, green, blue, and red. So if we needed 10 or more, we'd have to do a pretty big sample size. So that's why with chi-square, you can go with 5. 5 is kind of the number here. And then you usually want to check your 10% condition. That wasn't written here, but we're going to do it anyway. Does 50 represent 10% or less of all M&Ms? I think it is incredibly safe to say that that is true. So those are the 3 conditions you want to check for a hypothesis test based on chi-square goodness of fit. Random, large counts, and remember, large counts is greater than or equal to 5. You also want to check your 10% condition. Now, if it's an experiment you're looking at, that happens, you don't have to deal with the 10% condition. That goes out the window if it's an experiment. I'll even put that here. Don't need for experiment. All right, so now we have the option of calculating a p-value. There are a number of ways we can go about doing this. This refers to the table. I'm not going to refer to the table in this case. What we're going to do is we're going to use some calculator functions here. Now, the degrees of freedom represent the number of categories. And we have one categorical variable, right? But that doesn't mean we have only one category. Again, that's the number of colors here. How many colors did we have? We have 6 colors. So degrees of freedom, you can do 6 minus 1. That gets you 5. What's the test statistic for this test? That is our chi-square statistic. That would be 36.06, which we previously calculated. Now you can use table C for this, or you can use a calculator function. I'll walk you through how you can use the calculator to help you out here. Whoops. Get rid of that. Oh. I'm going to pull the calculator right up here. I'm trying to make it bigger. Let's see if I can do that. There we go. That's what I was hoping to do. So now they're both side by side. You get a little bit, you can see it a bit easier. Here's what I did. You can go to Stat. You can go to Edit. And then you can make lists. What I did was for list 1, I made that all my observed values, what did I see? My list 2 was what did I expect? And I entered all those in to the list right here. And you can do the same on your calculators. Once you do that, you can hit the Stat button. Go to Tests. And you're going to scroll down to chi-square goodness of fit. It's going to be way down there, right here. Now, your chi-square goodness of fit test on your calculator, by default, it's going to be observed values in list 1, expected values in list 2. So as long as you enter in everything like that, you should be in good shape. It'll probably ask you for degrees of freedom. Mine doesn't ask for that. My degrees of freedom here are 5, so make sure you enter that in if it asks you for that. If not, then you should be all set to go. So it all depends on which calculator you're using, of course. So this is one option you can do for it. Yeah, mine asks for degrees of freedom. Maybe yours does too. And then once you hit calculate, enter, you will notice that it gives you your chi-square statistic, which we calculated here, 36.06. That gives us our p-value. You'll notice your p-value. It says 9.22. Do not write 9.22 for your p-value. Here's the reason why. Look to the side here. It says E negative 0.7. That means this is in scientific notation. So that is 9.22 times 10 to the negative 7th power. It means you'd have to move that decimal 7 places. 1, 2, 3, 4, 5, 6, 7. That is a very, very low p-value. The probability of seeing the distribution that we got with our M&Ms, if this is true, if what M&M's is telling us is true, that they really give us 13% brown, 14% yellow, 20% orange, 16% green, and so on, if that's really true, the probability of getting the distribution that we got, including the 20 red M&Ms, is 0.000009. That is an incredibly low percentage. With p-values, just like all hypothesis tests we've been dealing with, we usually use a significance value of 0.05. So nothing that hasn't changed yet. For our p-value here, so what we can say is it is less than 0.005. So here's the conclusion I can come to. Since my p-value, yuck, the writing is awful. I'm going to use a better stylus, but it might make some noise, so bear with me. Since my p-value is less than, I reject my null. And if you remember in the previous video, the null that we established was that the proportion or distribution was as advertised, that M&M's was telling us the truth. But since I reject my null hypothesis, I have enough evidence to prove the distribution is not as advertised. I'm just putting it down here too, so I have a little more room. So we've proved that this hypothesis test is that M&M says that's the distribution. We got something wildly off. So based on what I found, I could say I have enough evidence to prove the distribution is not as advertised. Maybe yours was a bit more in line than mine was. Maybe you got a low chi-square statistic and a higher p-value. There's another way you can find your chi-square statistic. I'll walk you through it. If you go to second distribution, scroll down here, ChiSquareCDF. You can use this function as well. Oh, let me get out of here. Delete everything. Oh, let me get out of here too. Challenges of remote learning, right, guys? All right, let me try this again. I'm going to go to back. I want to do second. I'm going to go to distribution. If you go to ChiSquareCDF. All right, so you want your lower. Your lower is going to be whatever chi-square statistic you got. 36.06 is what I got here. And then for your upper, you want to make it like a really high value. Like, like infinite high. And then for your degrees of freedom, again, just plug them in. In this case, we had 5 because you take number of categories minus 1. And look, we get the same value here. That's another way you can arrive at your p-value. Now, how is this based, right? I'm going to pull this up. Let's see if I can get rid of this. I can't do that. That's all right. Now, chi-square distributions look something like this. Remember, they are only positive values, right? So you're going to get distributions that look like this, or it might look like this. All depends on how many degrees of freedom you have. The more categories you have, the more it flattens out. Here's the reason why, right? Say you had degrees of freedom of 1. You might expect to see something like this. Why? Because you really wouldn't expect to see that many differences, right? If it's only 1 category or 2 categories, you really shouldn't be getting a very high chi-square statistic. Whereas if the more categories you have, right, you can see more differences. So you get, maybe it looks like that. Like say for degrees of freedom of, let's say, 8. As opposed to 1, which might look like this, where you'd be accepting less chi-square statistics because you really shouldn't be seeing that many differences. If you have more categories, you can accept more chi-square values because you can accept more differences. Again, because chi-square, what you're doing is you're trying to find the probability of getting your distribution after they give you an advertised amount of, distributions or percentages. What's the probability you get these percentages if these percentages are actually true? And that's what chi-square goodness of fit is all about, and what chi-square in general is all about. You're trying to see how distributions fit into each other. So for chi-square goodness of fit, just a quick recap. 1 categorical variable. You find what you observe, what you expect, and then your chi-square statistic is what's the probability of seeing what I observe if I should be expecting this. And if you get a p-value of less than 0.05, again, the probability of seeing your distribution is less than 5%, then you can reject your null hypothesis, and you have proven that the distribution that they advertise to you is not true. You have enough evidence to prove that.